have brought my mouse so I can make sure we have both mouse control. Sorry about that, Michael.
Hardest time finding parking.
Yeah, just have a seat. We'll be there somewhere. Seeing you. Okay, so we got everyone in person here. Okay, how do I get rid of this Zoom thing so I can actually get my notes? Okay. All right, so on Monday we got to the point where we start talking about these Feynman diagrams, right? Specifically these vertices. I'm gonna use a little highlight thing. No, it's not right. Right, these vertices, right? And as you remember, the left one here is the electromagnetic vertices. There's the strong vertices, and then there's the weak interaction, which actually has two different types of boson that can actually couple to it. Okay, so those are all the possible vertices you can draw in the standard model, and some of them are allowed and some of them are not allowed, and we're going to see how that's going to play out in our little activity, and then also one of your homework problems that just got posted. Okay, and the idea of these vertices is that you combine these two vertices together. For example, in this little diagram, right, where the top half is one of the vertex, the bottom half is another vertex, and this allows electrons to basically scatter off each other. It doesn't have to be electrons; it could be muons scattering off each other, neutrino, whatever, right? So you can make all types of Feynman diagrams out of these vertices. Okay, and in this notation here, right, people call this the T channel. I don't know why it's called T, but yeah, I think it's just they started with S and then T and then used the next letter. I think that's why how it came about. But this is called a T channel. There's no rhymes or reason why it's called T. But the idea is that you have two particles coming in. I'm going to call this electron 1, electron 2, even though we cannot differentiate them in real life, right? Okay, and they scatter off each other. Electron 1 stays on top, electron 2 stays on the bottom, right? There's also this U channel. What happened in the U channel is that the position of the outgoing particle momentum actually swapped places, where instead of the electron 1 going to the top, the electron 1 actually went to the bottom instead. And you just can't, in cases of identical particles, you need two electrons. You cannot tell the difference between the two electrons. Therefore, right, in quantum mechanics, what happened is that if you cannot tell the difference between the two processes, you're going to have to sum up their amplitude together and then square the entire amplitude. And that's how you calculate the probabilities. Okay, we're going to see a little example of this with quantum tunneling in a second here.
So if you can't discern each channel,
right,
so by adding the amplitudes and then squaring them, say,
right,
then that produces the probability of
right,
identifying.
And remember that one of the key things, right, is something that we learned from hopefully somewhere in grade school, right? So like A plus B, the whole thing squared, is not equal to A squared plus B squared, right? So that's the difference between them, right? So you have this cross term that's going to have this can cause constructive or destructive interference between the two processes. Okay.
There's also the S channel, right?
Right. That's gonna. So I copy and paste this, so I have to draw the S channel again. Okay. So the S channel, so you guys have good memory, right? It's kind of the annihilation channel where you have, let's say, an electron coming in like this, okay, and a positron coming in, plus, okay, I'm not drawing the arrow yet. They annihilate to create a photon, or actually a Z, also it's also possible, and then spew out other things. In this case, you can have, let's say, like a muon coming out instead, okay, mu minus. Okay. All right. Notice that I have not drawn the little arrows on this diagram yet. Right. The idea of this arrow is that, right, the electrons are coming in, so an electron is a particle as opposed to an antiparticle. Unfortunately, we don't have the mathematics to describe why there's particles and antiparticle yet. We're going to see that when we get to chapter 4 on the Dirac equation. But, right, the positron is an antiparticle, right? So these arrows are actually tracking an antiparticle coming into the vertex. So an antiparticle coming in the vertex is as if a particle is going out of the vertex. Okay. So these little arrows are tracking particleness. Okay, so I don't think they use that term, but it's a good analogy. Okay, and then since a muon is a particle, so that would be going out, and then an anti-muon is an antiparticle that's going to be shown as coming in. And you notice that these straight solid lines represents the fermions, right? And there's always one fermion going out, going into the vertex, one going out, no matter what. Okay, you don't have two coming in like this. Okay, it conserves this fermionness of things. Okay, and the squiggle lines represents the gauge boson. Okay, in this case, either a photon or a Z. Okay. And remember, these things in the middle are virtual, right? Meaning that we never actually observe them ourselves. So that's why they're called virtual particles. They get
Particles are just particles of opposite charge, whatever the
opposite electric charge, yeah. Yeah. And that's gonna come into play. There's a little bit more detail about that. We'll see that when we get into neutral particle can also have antiparticles. There's an anti-neutron also. Okay, but just to give you guys a little bit of a segue into the next thing, right? We're talking about, how often does the T channel happen? How often does the Q channel happen? How often does the S channel happen, right? Because you need to figure out how often these things, how probable these things are in order to make calculations with them. There's something on chat. Oh, okay, sorry. So I think I'm going to let Alex take care of the track, so I'll not jump to that on and off. Okay. Okay. So I just want to give you guys a little taste of like how in quantum mechanics these probabilities are calculated. And the example I'm taking is from the modern physics textbook, which I think most of the San State students have taken and got through this chapter, but maybe some of the other students from other universities do not have seen this particular chapter. Okay, and this is the quantum tunneling chapter. So yeah, I put it somewhere up here. Oh yeah, I need that. So that okay. The idea is that you have a particle, right, coming from the left, and it's gonna hit a barrier. This little gray part is a barrier. Okay, and this is not a physical barrier usually. Usually it's like, maybe like a nucleus that has the same charge as whatever is coming in, and then therefore they're actually repelling each other, or some sort of barrier like that. Okay, and the idea is that, well, in classical mechanics, if the energy of this barrier is higher than the particle that's coming in, the particle is just going to bounce back, right? It can never penetrate. But in quantum mechanics, there is a chance for it to penetrate through these barriers, okay? And the way you figure this out is by declaring the wave function in the three different regions, psi1, so this is the Greek letter psi, and so this is on this side, the incident side, and then psi2 is what happens to this wave function within the barrier itself, and then psi3 is what happens on the other side. And the thing you're actually interested in is what is the chance of a particle coming in like this over here as a wave, right? Particle wave duality, and what is the chance of it getting through that barrier and going through? Okay. So what we're going to do is we're going to define the wave function in region 1 as some wave function that has some amplitude A, right, going forward, propagating to the right. I'm going to draw a little arrow here. Okay, so e to the I kx minus omega t, right? That hopefully is familiar with everyone. Where this is just the Euler, is it called an Euler formula or Euler something with Euler? Okay, equation or formula that is just representing sines and cosines, right? It's just with a particular frequency omega, right? Okay. The one with the opposite sign, well, actually the same sign between the k and the omega part, that represents the wave going to the left instead, right? Okay. Okay. And region 2 is a little bit special because instead of just a wave, what happened is that this wave is going to be exponentially decaying, right? The more you go into the barrier itself, the less likely it is to get to that part. Okay. So therefore, in this case, you have this alpha to it. Okay. Instead of kx, you have alpha x. Okay. and therefore you're gonna have an exponential decay within the barrier itself. And the important thing is actually these constants that's in front, right? A's, the B's, the C's, and the D's. Okay. On the other side, what's going to happen is that we're going to describe the wave as a wave that's going to the right, right? Once again, so we have this amplitude of this part of the wave F. Okay, and also, right, just to be general, we could also, well, you can tell me whether or not there could be a wave going from the right to the left in region 3. So those of you who had this class recently are not allowed to say anything because you might remember this. Okay. So with that information, right, what is this constant G equal to? Can you just tell us right away? So this amplitude G. Anyone on Zoom? Maybe? Is it possible for the wave to come back from right to left here? Right? When there's a wave passing through it. Oh, yeah, I need to record. And oh yeah, this.
So we have in the chat Bahare saying that it's 0.
Right, exactly. Right? Because there's no possible, if you have just a free particle here, right? Once the wave gets through here or the particle gets through here, right? There's no way for a wave to come back the other way, right? There's nothing for it to bounce off of afterward. Well, at least in this system, there isn't anything. So right away, we actually know that amplitude G is actually 0. And in this particular chapter, the thing you're interested in is that how probable is the incoming particle getting reflected, meaning this this ratio R, right? And to calculate this in quantum mechanics, what you do is you basically square the wave function. And when you square the wave function, basically the wavy part, the e to the I minus e to the I kx minus omega t part just kind of, gets product to 1, right? And what you're interested in is actually the amplitude square of these wave function divided by each other. Okay, so this is the part that's been reflected, right? That's the amplitude square reflected. This is the incident wave amplitude squared. Okay, and we're going to see why this is going to be useful for us when we start talking about particle physics. Okay, incident. Okay, I can't spell incident, but you know what. Okay, and the thing you may want to calculate also is like, what is the chance for it to transmit, right? The probability for it to transmit. So both of these numbers are probabilities, right? Okay, so the ones that are transmitted, right? The only wave that's in region C is proportional to this, amplitude F, right? And the part that's incoming, right, is actually proportional to the amplitude A, right? And therefore, if you want to figure out the probability for the particle to get through the barrier, right? Once again, you square these wave functions, okay? And then, but the thing that actually matters is the amplitude square between the two wave functions, okay? And that little star here, just to be careful, does not mean multiplication, like in Python or something like that, or computer programming. That actually means the complex conjugate. Okay, so B star is the complex conjugate of B. Okay, and if you have questions about complex conjugate, just we can talk offline, but it's not going to be super important here to actually do the actual math. But just trying to get this little concept across. Okay, it's this amplitude square that matters, right, when you're calculating probabilities. Okay, so in modern physics, the way you guys it was done is basically you assume all these particles are like spin 0, so you don't have to deal with spin at all. Okay, but as you learn from Monday's lecture, all the fermions have spins on it. All the gauge boson has spins on it. And what's going to happen is that instead of these amplitudes being, complex numbers, okay, and where you can actually figure out the probabilities by just taking the complex conjugate times itself, due to the spin nature of most of the particles in the universe, what's going to happen is that it's going to make these amplitude, instead of complex numbers, is going to turn them into complex matrices. Okay. So you're going to have to do matrix multiplication in order to calculate these things. And we're going to see this when we get to the direct equation in chapter 4. Okay. And this just comes out naturally. It's like, oh, well, it doesn't work with just numbers. We have to use matrix, otherwise all the math comes in. Okay. And that's the sort of like the very, I don't want to say that the word magical, but like sometimes just something fits together so well that it's as if, you know, it's magical. Like, and I'm sorry?
Too good to be true.
Well, it is true. That's the thing, right? And it just fits together. And this is one of my favorite thing about particle physics is that you do a bunch of math on a piece of paper, and then at some point, you know, maybe a year later, 10 years later, someone makes an experiment and say, oh yeah, what you wrote down is actually true. Okay, and which is extremely fun. Okay, okay. So in these cases of scatterings, going back all the way up here, sorry, I should have kept these have a copy of these diagrams down here, right? Okay, each of these scattering vertices is going to have an associated, instead of a complex number, it's going to have to be associated with some matrix. Okay, okay, which like in places of it's basically the matrix amplitude of these things. Okay, so since I can actually just draw a diagram of it here, right? Let's do the electron scattering of each other. What channel is this, by the way? I'm gonna write that. Anyone? Anywhere? T channel, right? Okay. So this particular diagram, okay, in this case, right, since it's a electromagnetic interaction, this will be proportional to G. I'm gonna write G sub E, and this one's also electromagnetic, so it's actually also G sub E. Okay. This G, right, basically tells you kind of like how strong this coupling is between the electrons and the photon. Okay, so if you were looking at this diagram, what's going to happen is that, well, there's a factor G here, there's a factor G here, right? To figure out the matrix amplitude of this particular diagram, okay, this the matrix, the squiggly M here, okay, people call this the matrix element, but you know, but you can think, I think of it as just like a substitution for the complex amplitudes. Okay. For this tree level diagram, so a tree level diagram is one where you have just a single exchange of bosons between the two fermions. Okay, so for this tree level diagram, since there's two factors of G here, so this particular matrix element is actually proportional. So that's not an alpha sign; that's a proportionality sign. It's proportional to G squared. Okay, I'm gonna have a little bit of fun. Okay. So to make things easier or harder, especially for students, harder for students, easier for people who've done this multiple years, we're going to define a new quantity called the coupling strength, as opposed to the coupling constant. We're going to call something coupling strength, and we're going to make that letter, just to be even more confusing, call it alpha, because it looks like the proportionality sign. Okay. That's the fun we get this, right? Okay. So, and it's actually these alphas that you can measure in an experiment, because remember, you never actually measure one single vertex, right? You always have this diagram together, so you actually, the minimum you can measure is actually basically G squared. You can never actually measure G itself. Okay. Okay, so in modern physics, when we were calculating this quantum tunneling probabilities, right? We have to calculate the amplitudes squared, right, in order to calculate the probability. The same thing happened in particle physics. In order to calculate the probability of this, you don't want the matrix itself, you want the matrix squared, right? Okay. Therefore, this little weird, this is the capital gamma, Greek letter gamma, is called the transition probability, or the transition rate from the electron coming in and being scattered or not, okay? Since it's proportional to the matrix squared, okay? Instead of being proportional to alpha, it's gonna be proportional to alpha squared, okay? So it's always alpha squared that, well, for tree level diagram, it's alpha squared that you actually care about in order to figure out what is the chance of that happening, okay? If that's really opaque right now, just think about what is the chance of your little particle passing through that barrier and transmitting on the other side, right? That's the analogy I wanted to go back to in quantum physics.
I think we have some online questions.
Yes.
So
Yes.
Bahare, did you want
Yes, Dr. Wing,
to just unmute yourself?
when we are calculating the probability, are we calculating that for the whole system or just for one vertex?
For the entire, you have to calculate the entire diagram. This
Oh,
this
okay.
diagram has two vertices. That's why it's proportional to G squared, which is defined to be alpha, and then alpha is actually has to be squared also because of the matrix element squared.
So the alpha then should be alpha 4 to the power of 4.
Alpha squared. Oops.
Okay.
I think it just is alpha squared or G to the fourth.
Oh, G to the 4th. Yeah, I meant, yeah. Okay.
Yeah, and can I just add one thing? So just to be clear, and you guys will see this when you start to do homeworks, and I think when we start doing exercises today. Right, so what we're really doing is we're building up these diagrams using these vertices. And ultimately, there are lots of different diagrams that you can draw for the same process. So we're seeing, for instance, even at this tree level where we just sort of have one exchanged particle, even at the tree level, there are sometimes multiple diagrams you can draw. We can have an S channel and a T channel. And so there's going to be some amplitude associated with each total diagram. So not just the vertex, the total diagram. And then we want to add up, ultimately we'll add up all of the possible diagrams, and then square that to find the probability. And it turns out these tree level diagrams, because they have the smallest number of vertices, are the ones that are going to have the highest probability or the highest amplitude that they'll contribute. I'm sure eventually we'll see some more complicated diagrams, which it turns out will have decreasing importance in your calculation. So we can sort of approximate them as being 0 in certain cases, because they'll just be so much smaller in terms of contributions.
Yeah, so that's true for electroweak interactions, but for the strong interaction, we're gonna run into trouble because and that's
Yeah, the strong one makes things hard. So good point. Yeah.
Okay, let's talk about this coupling constant thing, right? If you look up in Wikipedia, this is for electricity magnetism. This is actually known as the Planck structure constant. You may have heard this in your modeling class also or not, but don't worry about it. We'll just define it here, right? This alpha is actually alpha of electricity magnetism. Okay, it's equal to the charge of the elementary charge squared, right? And then there's this 4 pi epsilon factor that you find everywhere whenever you deal with electricity magnetism, right? And divided by, you know, the Planck's constant, the thing's called the reduced Planck constant, right? Where it's Planck's constant divided by 2 pi, right? And the speed of light, okay? And if you plug in all these numbers in SI units, the electron charge, epsilon, h bar, and speed of light and everything, right? You're gonna come up with a number that's gonna be 1/137. And the unit for this number is nothing. There's no u values. It's 1. Okay, it's actually a unitless quantity, which is really nice because what's going to happen is that when you convert to a different unit system, which we'll do hopefully by the end of today, this constant remains the same number. So no matter what, you can use, you know, SI units or imperial units, whatever units you want to use, right? This number always comes up to be the same number, which is really nice. Okay, so for electromagnetic interaction, this number is 1/137. Okay, so as shown in the tree level diagram process here, right? That's the one we're looking at a lot. Okay, and as Dr. Miller actually mentioned, right, there are other diagrams that you could draw. Okay, and the example the book gave is this second order diagram, where instead of just the electrons scattering off each other, what's happening is that the electrons scattered off each other twice by exchanging 2 photons instead of just 1, right? And essentially, you can have them exchange 3, 4, 5, infinite number of photons. Okay, and I think this coupling constant being less than 1 allows us to do calculations with it to fairly good certainty by just dealing with the tree level diagram. Because what's happening here is that, well, remember this tree diagram, right? I don't like this letter G. Okay, so this is a coupling constant G, G sub E here. Okay, but over here, how many of these coupling constants do we have? Got 1 here, 1 here, 4, right? So that means the matrix element, okay, for this particular diagram is going to be proportional to G e to the 4th power, which is equal to alpha squared, right? Square, okay. And once again, you have to square these matrix elements, right? So square that explicitly. Okay. So when you square this, what happened is that for 2 photons to be exchanged between 2 electrons, okay, the probability of that, so remember matrix element squared gives you the probability, proportional to the probability, okay, is actually alpha to the 4th instead, okay? Okay, the single exchange, photon exchange is alpha squared, right? And since alpha EM is 1 over 137, you can actually calculate the ratio between these things, okay? So the probability for having 2 photons exchange between electrons versus the probability of having just a single photon exchange electron is going to be proportional to, well, alpha to the 4th power on top, alpha to the square on the bottom, right? If you check through your calculator and do all this stuff, you get a number that's 5 times 10 to the -5, or about 1 in 10,000. Okay, we're going to just do order of magnitude. Okay, so the probability of a electron scattering once off each other, go away. Sorry, not you guys, the little screen thing on the screen. Okay, the probability of a photon of 2 electrons scattering off each other by exchanging only 1 photon is 10,000 times more likely than a pair of electrons exchanging those photons twice instead. So essentially, if you can calculate what this number is, you have a result that's good to 1 in 10,000. Okay? And which is why we mostly worry about tree level diagrams, and I'm going to see how this breaks down in other interactions. Okay. Okay. So the same can be done for the weak interaction, where this alpha weak, instead of being 1 over 137, is actually even smaller, 10 to the -4. Okay. The weak interactions are also nice to calculate, because since this is going to be the next order diagram is going to be 10 to the -8 times less likely to happen, right? Because you're basically always squaring this this alpha. Okay. However, in the strong interaction, the alpha for the strong interaction is actually 1. Well, approximately 1. It depends on the energy. It actually changes as a function of the energy of the interaction. And then, so now you get in trouble because, right, if this was a strong interaction, right, the ratio between these 2 diagrams is going to be 1. So every diagram is important, right? If you're exchanging 1 gluon between quarks versus exchanging 2 gluons between quarks, both of those diagrams are very important, right? So, okay, well, I can do 2 diagrams, but then you can exchange 3 gluons, 4 gluons. So you have infinite number of calculations you need to do in order to predict the probability of a single scatter. Okay, so this takes us to our little activity that I want to just have you guys get started on the homework. But so this is one of the first homework problems, or maybe the second one now. Okay, so those of you, especially those of you who have your laptop out, if you want to join the growth MSI Zoom and just be maybe on the opposite side of the room. So Alex, do you mind making I think there's 17 students, I think.
I don't know that I have permissions to do that because I'm not the host.
I can make you co-host right now. Okay, I guess I have to do this every time or something. Okay.
So we have 7, or I guess I'll wait till all of your local students join before making the breakout rooms.
So we have 6 students here and 10 students online. Let's just make 5 breakout rooms. Okay.
Okay, great.
Okay, and you can make them you can self-select into them.
Okay, instead of doing it randomly.
Make them randomly, but and then I'll just have the students who are here join, if I was in there, if I got assigned to it, and then the room itself got assigned. Okay,
Yeah, yeah, and great.
let's just do it random. Okay.
So you should have all, oh, sorry, I gotta open the rooms. Okay, so you should all get a request to join breakout rooms right now, which currently it's groups of 2 or 3. As people join the meeting, I'll add them into rooms.
So those of you who don't have your laptop handy, you can go ahead and use my laptop or just use the rooms. Just use my laptop, and I'll join one of the rooms because I think I got assigned. I'm gonna join room number 4 because there's only 2 people.
Do we want Wing